Yeah. Say that what? For the table. Yep, this goes in your table for question number 31. All right, Lorelei, I've got a lot of technology going today, so I am video recording this in case it gets a little glitchy between sending it up to the whiteboard for the class to see and collecting the data and sending it through Google Meet. So if it gets a little glitchy at some point, I'll just send you a video of the lesson, and that way you can look at it. Yeah, I think I saw one back there. Oh, yeah. Can I make it bigger? Let's try it. So the way this instrument works, it's basically a little oven, and it's called gas chromatography because it's going to vaporize any chemicals that I put in there within reason. So it's not like I could put a solid in this instrument and it would just liquefy and then vaporize it. So really, we're dealing with organic liquids that vaporize fairly easily. So the starting temperature is going to be 65 degrees Celsius. This right here, room temperature is about 25. Body temperature is about 37 degrees Celsius. So it's fairly warm. Not so warm that you'd burn yourself. But again, that's enough heat to vaporize the liquids that I put in there. It's going to hold that temperature for 2 minutes. In other words, it's going to let that chemical vaporize. And then what it's going to start doing is it's going to start ramping up the temperature 10 degrees Celsius every minute. So after 2 minutes, it'll be at 65 degrees Celsius. After minute 3, it would be up to 75, and then 85, then 95, then 105. So it'll keep heating up. We're going to stop the temperature experiment at 120 degrees Celsius. That would be hot enough to get any of these chemicals to vaporize. It'll hold that temperature for up to 12 minutes if we need it. So at this point, we could run an entire experiment for 25 minutes. Don't worry, we're only going to be here about maybe 2 to 3 minutes per sample. So we'll definitely shut it off early. And then the fan you probably hear blowing in the background is the pressure that we're talking about. If we were using the professional model of the GC, which are in the back rooms, there's big brown boxes about the size of a microwave. They kind of have a blue front to them. Those are kind of the professional models of the gas chromatographers or the GCs, and they use helium gas to run through. But the revolutionary thing about this one, even though it's a little less high tech, it's a benchtop model and it doesn't require any helium. It just pushes some air through to help those molecules race through the instrument. Just to give you some perspective on these kilopascals, if you kind of wave your arms, this sky sitting on our heads is 1 atmosphere, which is about 101 kilopascals. So to put that into perspective, it's only giving it just like a little extra puff of air, 15 kilopascals out of 101. So it's just a tiny little extra breeze helping to blow those molecules through the instrument. As far as what is on the inside of this instrument, there's a heater. This is a column out of, now we call it a column, it looks like a coil. This is a column out of our professional GCs. But what happens is the molecules will start racing through. I'll make this a little bit smaller. There we go. It's going to start racing through this coil or column. And when it flies at the other end of that coil, it'll hit a computer chip detector, and it'll signal some sort of like millivolts. And when the computer detects that, it'll plot that up on the graph. Oh, love it. There we go. So again, this is the coil or the column that we're talking about. As far as paper chromatography, if you've already done that lab station, you can think of this column or this coil kind of like the paper. You put the colored marker at one end of the paper and the colored dye travels up the paper. It can go a different distance, it can go farther up the paper. or less distance up the paper. What we're actually going to be measuring in this experiment would be time. How long does it take the chemical to fly through this column here? Any questions on that? All right, so let's go ahead and set up our experiment for data collection. I'm going to hit done. Now, right now, you can see it's starting to heat up. Obviously, it's at room temperature, which is 25 degrees Celsius, but that's not quite hot enough to start the experiment. So it'll let us know when we're ready to start the experiment. I'm trying to minimize this a little bit so that people at home can see, but I'm not having a lot of success. I might have to wait till this window is done. All right, so now as far as question number 30 goes, how do we get this instrument all ready for data collection? So I have my first chemical up here. This is my methyl alcohol. This is the graph that you're going to draw on question number 32, but I have to prep the sample. So to get that sample into the instrument, I'm going to use a micro syringe. So you can put that down for question number 30. This is called a microliter syringe. If I filled it up all the way, it would have 1 microliter of sample. That's a millionth of a liter, or 1/1000th of a milliliter. That's not a lot. So I'm going to rinse out my syringe several times with my first chemical. So I pull the plunger up, and when I push the plunger down, you can see basically nothing comes out, just the tiniest little drop, 1/1000th of a milliliter. That's all this sample needs to analyze the sample. So I'm going to do that several times. Pull the sample up, get rid of the sample. Pull the sample up into the syringe, get rid of the sample. Again, it's just the tiniest little drop. And now I'm going to pull the sample up one last time. This is going to be the sample that I use to inject into the instrument. All right, you can see now our GC is all ready to go. We're at 65 degrees Celsius. We're at 15 kilopascals of pressure. Now, the thing is, with this syringe, even 1 microliter is too much chemical. I can get away with 0.1 microliters. That's a 10,000th of a milliliter. So I'm going to push the plunger until I get to the 0.1 mark. Basically, a fraction of a fraction of a fraction of a drop of chemical is all we need to analyze this sample. So I'm going to push it into the instrument and simultaneously, or as closely as possible, hit the collect button. All right, I'm probably going to be a couple seconds off, but that's okay. Yeah, that's what I want to do. Okay. So you can see the computer is measuring the millivolt signal. Right now, this is basically nothing. Nothing's hitting the detector. And it's measuring the time basically several times a second. So that chemical has been vaporized. It's running through a little tiny column that looks like this. It's running through, and when it flies out the other end and hits the detector, whoa, we got a peak up there. That peak is the chemical that just hit the computer chip. So right now you need to basically, for question number 32, draw a picture of that graph. You don't really need any numbers on the x-axis or the y-axis. Just label the x-axis as time in minutes. Label the y-axis as signal in millivolts. It's an electric signal. And then just draw a graph that looks like a big mountain peak. Yeah, it looks exactly like that. Again, I don't need all the numbers on there. You want to know that time in minutes is on the x-axis and signal or millivolts is on the y-axis. And that's how fast it was. Now, what we care about is how long did it take that chemical to run through the instrument. That's called the retention time. The one number we do want to label would be this number right here. So let me stop collecting data. Obviously, we don't have to let it run for 25 minutes. I'm going to highlight this peak right here, and I'm going to ask the computer, well, what time did that peak occur at? You can see this right here. The retention time was 0.655 minutes, just over 30 seconds. 0.655 minutes. So I'd like you to label that peak for methanol. It's an alcohol that has 1 carbon at 0.655 minutes. And that's it. Any questions how that works? So I have 2 more samples to analyze. Question number 33 would be 1 propanol. That is a 3-carbon alcohol. And then we'll do number 34, butanol, which is a 4-carbon alcohol. So if we go back up to question number 30, how do I get this reset for the next chemical? I'm going to hit start. It says, do I want to store the latest run? Yeah, we'll keep it on the screen. Can you just double check my temperature profile? Are these numbers all the same? We're good? Okay, so I'm going to hit done. It needs to reset itself. It needs to heat itself back up. So in the meantime, I need to clean my syringe. So I'm going to clean it with acetone. So that would be something I would add to question number 30. You need to clean the syringe. It's a really expensive syringe. And if it gets clogged up with chemicals and gunked up, it'll probably snap. Any guesses how much this syringe costs? About $100, yeah. It is super, super, super fine. Like the needle inside is about the thickness, probably pretty close of a human hair. So yeah, we got to be really careful with it. So I'm just going to soak up some fingernail polish remover, some acetone, and I'm going to squirt it out. And again, you'll see pretty much nothing come out except that tiniest little drop there. We'll do that 2 or 3 times to clean it out. It's called acetone, A-C-E-T-O-N-E. Acetone. All right, now as far as my next chemical, it's going to be N-propyl alcohol. Joe, you had a question? No. Okay. Now, would you agree there might still be some acetone left in this? So what I'm going to do is I'm not going to test the very first sample I pull up into my syringe. I'm going to wash it with my propyl alcohol. So I'm going to pull up the chemical, get rid of the chemical, pull up the chemical, get rid of the chemical, pull up the chemical, get rid of it, and we'll do that one last time. So I pull up way more than what I need. I have way more than 1/10 of a microliter. Again, that's 1/10,000th of a milliliter. And now that the instrument is ready, I'm going to push the plunger to the 0.1 microliter mark. And now I'm going to inject the sample into the GC and as quickly as possible, press the collect button. This is where it's nice if you're working with a lab partner. On the count of 3, 1, 2, 3, you go, and they press collect. Again, we might be off by a fraction of a minute, but that's okay. So now a new chemical is racing. Because this molecule is bigger, you think it'll run the sample thumbs up faster or thumbs down slower? You think a bigger molecule would go faster, thumbs up, or slower, thumbs down? Yeah, kind of like a tractor trailer. A bigger molecule, it's bigger, it's bulkier, it'll probably stick to a lot more things inside that column. You can see we pretty much already passed the 0.65 minute mark, and there's no chemical being detected. Getting super close to a minute. Oh, start to see a peak. So we have a new peak for a new chemical, and sure enough, it did take the chemical longer. So for question number 33, you're going to sketch the exact same graph, just move your peak a little bit farther to the right. While you guys are doing that, I'm going to clean my syringe with acetone. So you can see our signal is pretty much back to where it was. If this was my last run for the day, I'd probably let it go for maybe 2 more minutes to finally push all of that chemical out of the column. We don't want any chemicals getting stuck inside the column, clogging it up. But I think because I have a couple more tests ready, I'm going to hit stop. We'll do the same thing. We're going to analyze this blue peak. And if I zoom in, you can see that maximum peak had a retention time of 1.175 minutes. So just over a tenth of a minute, basically 66 seconds. So 1.175 minutes. All right, how do you think the retention time for butanol is going to compare? It'll have a longer retention time or a slower retention time? Longer retention time or shorter retention time? A bigger, bulkier molecule will probably take even more time to exit through the column. So let's go ahead and get that set up here. I'm going to scale this out so we probably don't need to go up to 25 minutes. Let's just go to, we could probably stop at 5 minutes. Yeah, that kind of zooms in the graph a little bit. Cool. So I have to clean my syringe again. And I'm going to hit start collecting data just to get that same temperature profile. We're good to go there. It's going to heat back up. And while we're doing that, I'm going to fill it with the butyl alcohol, which is a 4-carbon alcohol. It smells a little bit like vomit because butyl alcohol is pretty similar to butyric acid, which is the major scent molecule found in vomit. So I'm not going to leave that bottle open too long. Has a little bit of a buttery smell to it because that's where butyric acid got its name. It stands for rancid butter acid. So it smells a little bit like buttered popcorn. All right, any questions so far? So what we're going to do is we're going to do our third chemical right now. So we'll have a graph of each chemical, and then what I'm going to do in question number 35 is I'm going to do an unknown mixture. This is the beauty and the power of this instrument. When I put some chemical in there or chemicals in there that we don't know what they are, this graph should be able to match up pretty closely and help us identify what it is. All right, so you can see our G is all ready to go. I'm going to get how many milliliters? 0.1 microliters, which is a 10,000th of 1 milliliter right there. I'm going to inject and press collect. So same sort of thing, it's running through, it's timing how long it takes the chemical to run through, and a lot of us had this idea that this might take even longer to run through because it's a bigger, bulkier molecule. It's a stickier molecule. That's going to be actually a whole chapter that we discuss in about 3 units. You guys already know about hydrogen bonding, but there's other attractions between molecules that cause them to be sticky. There's London dispersion forces, there's dipole-dipole forces. We'll discuss all of that and talk about why these molecules are sticky. So we can see we've already passed the point for methanol. We're coming up pretty close to the propanol. And it looks like we've already passed that mark, which is a good sign because we were expecting this to be a slower molecule. There's people at Johnson & Johnson right up the road. They have these instruments, well, not these, but the fancier versions, even newer than those, running basically 24/7. They get chemicals in off the train. They want to make Listerine. They got to test those chemicals and make sure they are what they say they are. When they make their Listerine and all their byproducts, they got to test those chemicals to identify, well, we got another peak developing, to decide have they actually made the chemical that they were supposed to make. So, I mean, there's people, their entire career is to run instruments that look like this. Pretty cool stuff. So again, you're going to sketch a new graph for question 34. Obviously, the peak will be a little bit farther to the right, but basically the same graph. It's beautiful. Absolutely beautiful. So again, if this was the last run for the day, the millivolts are pretty much back down to normal. I'd probably let it run maybe 1-2 more minutes just to flush out all that chemical. I'm going to go ahead and stop it because we don't want to stop with 3 known chemicals. We want to run question number 35, the unknown mixture. I mean, this instrument is cool and it can tell you how long it takes a chemical to race through. But if you can use it to solve a real life problem and say, okay, we have some unknown mixture up here. Does this have 1, 2, or 3 chemicals in it? This instrument is going to tell us. So I'm going to hit stop. We'll hit start after saving the latest run. Temperature profile is exactly the same as it was before. That's pretty important because all these values and peaks would shift if I start increasing the pressure or changing the temperature. And while that is cooling down, I'm going to start prepping my unknown mixture. So I'm going to pull up the unknown chemical 2 or 3 times. Now I'm all ready to go. All right, so I need to push the plunger. So it says 0.1 microliters. Again, this entire graph is based on a 10,000th of a milliliter of sample. So it's great for a crime scene. It doesn't take that much chemical to actually inject. All right, 3, 2, 1, go, and collect. Sweet. So now we just sit back and watch the magic happen. Whichever peaks line up most closely, that tells us what those unknown samples are. Notice how I'm cleaning out my syringe for the last time. We just want to make sure it doesn't get clogged up. You can see we've already passed the mark for methanol. So there is, well, maybe we didn't. So it's definitely a smaller peak, but it looks like that is pretty close. I'm going to try to switch the color because that orange and the red look pretty similar. I think I can do that. Let's go with purple. And it looks like we have a second peak developing right now. Again, there's no guarantee the peaks will match perfectly 100%. But again, within reason, we should be able to identify what these unknowns are. We'll let it go maybe 2 more minutes just to make sure there's not a third peak. Thank you. So that purple graph is the graph you'd want to sketch for number 35. Oh, did I forget that one? Oh, we'll go back and get that one then. All right, so I can kind of do it manually. If you see my cursor here, if I put the cursor right at the peak, the X value would be the time. It looks like it has a peak of 2.166. 2.166. So yeah, that's a really important value to write down. So for question 34, butanol's retention time, the peak was about 2.166. All right, I'm going to let this keep running for several more minutes to flush out all of those chemicals. I'll probably, let's scale this down to 3 minutes. That's probably good. Perfect. So I'm going to zoom in right here on the first purple peak. That happened at 0.742 minutes. 0.742 minutes. So it's not a perfect match, but if you had to guess what chemical that was, what would you say? Methanol, yeah. So yeah, that is definitely the closest chemical to that one. I have a feeling it got slowed down a little bit because there were other chemicals in there. It probably wasn't as fast as maybe some of the other things. It probably bumped into some of them, maybe started interacting with some of those other molecules. And that probably is why it shifted a little bit to the right. That's not that uncommon. And for the last purple peak, which is 1.66 minutes, 1.66. If you had to take a guess at which chemical that was, what would you say? Mick? The propanol, the blue one? Yeah. Okay. You're saying that purple one is closer to that blue one? Okay, maybe. Yeah, I'd probably say it's definitely closer to that green one. So I would probably say if I had to take a guess, I'd probably go with 1-butanol. So if you could just label those two peaks with what you thought or decided they were, it seems like we're thinking it's 1-methanol or just methanol and 1-butanol. And if we take a look at the answer right here, it's probably a little hard to see that. It is methanol and 1-butanol. So again, using 10,000ths of a milliliter, we were able to accurately identify what that mixture was. Questions on that? All right, final question, number 36. Gas chromatography separates a mixture based on differences in which physical property? How did this whole thing work? Feel free to take a look back at your pre-lab. What determines how fast those chemicals race through the instrument? Sam? The size has something to do with it. Yep, that definitely affects this property. Not density. Okay, the temperature kind of, it's almost like distillation, the temperature at which it boils. Mass might have something to do with it. It's really the strength of the intermolecular forces. So intermolecular forces, how sticky those molecules are. Do they stick to the column as they're going through, or are they fairly unsticky? Now, I'm not saying what you guys said was wrong, because basically everything we talked about, boiling points, the size of the molecules, those are all based on intermolecular forces, but I'd say intermolecular forces is probably the best answer. So examples would be hydrogen bonding. These are all alcohols. They have that OH group on the end. They can definitely hydrogen bond. There's other forces of attraction, like dispersion forces. The bigger the molecule, the size of the molecule, the more intermolecular forces, the stickier the molecule is. It'll take the molecule longer to run through. with that being said, are there any questions I can answer about gas chromatography? Okay, so with the time that is left, let's go ahead and put your goggles and aprons on. Get the aprons out of your assigned lab station, and then move to whatever lab station you left off on yesterday. And let's try to get maybe 2 more lab